All right, so in our beginning look at volumes of solids of revolution, all the solids we looked at were just that. They were solid, okay? It was a big mass of something, and we had our magic yeast that I talked about, and we had all kinds of stuff that grew up out of the page, and then we spun stuff, and it was stuck to the axis. It spun around. Well, things aren't always stuck to the axis they're spun around. For example, on number 1 here, this isn't stuck to the x-axis. So when I spin it around the x-axis, I get a solid that looks something like this. It's got this like cone-shaped hole in the middle of it. All right, so it's kind of almost like a pointy bundt cake with a cone-shaped hole in the middle. No, I can't bake bundt cake for you. It's against the rules. But think about bundt cake, okay? That's a solid, but it's got a hole in the middle. So what we do is when we have stuff like that, to find the volume of something, what we do is we say, you know what? Well, before I spin this, I'm going to draw a representative rectangle right in here, and I'm going to spin it around the axis. And that representative rectangle is now going to look like this, with a hole in the middle. And I have what's called a washer. So instead of a disc, this is a washer. Please ignore how terrible my drawing is right now. But here's my washer, okay? It's 3D. It's got a little bit of depth to it. And then it's got all this solid stuff, all right? So if I want to find the volume of a washer, when we create a solid by revolving a region about an axis, and the region does not fully touch the axis, our cross sections look like discs with holes in them, or we call them washers. What you can do here is you can picture a hard-boiled egg, but pop out the yolk, okay? So if I took a hard-boiled egg and looked at like the middle part with the yolk popped out, all right, that's kind of what we're talking about here. All of our cross sections have a face of 2 concentric circles. So here's 2 circles. And if I wanted the area of that face so that I can stick with this volume formula, a of x dx, that's a piece of cake, because the area of a circle with a hole in it would just be pi r squared minus pi r squared. In other words, find the area of the big circle, the area of the small circle, and then subtract. So capital R being the larger radius, little r being the smaller radius. Therefore, the volume of our disk is the volume of a of x dx, which is the integral of pi big R squared minus pi times little r squared. Or you can pull the pi out in front and do it this way. What's important here is that you have to remember to square first, then subtract. Okay, so we square the radius first, and then we subtract, because I need to find the entire area of the big circle and then subtract the area of the small circle. You have to square first and then subtract. Speaking as an AP reader, if you subtract and then square, we pretty much just don't like you and write you off for nothing and you get 0 points. End of story, you're done, goodbye. Even if it's a 4-point question, if you don't square them first and then subtract, and instead you subtract and then square it, you're dead to us. We don't even look at it anymore. So please square the outer radius minus square the inner radius, all right? So if I want to find the volume of the solid created when I spin this around, I have discs that look like this. My outer radius, I'm going to draw in red here, my outer radius would go from the center of my washer out to this edge, which when it comes to the picture up here goes from the axis of rotation to the curve furthest from the axis of rotation, and therefore the length of this segment would technically be like top minus bottom, which would really be, well, let's see, my top curve would be cosine x, and my bottom curve is the x-axis, which is just technically y equals 0. So my outer radius is just cosine x. My inner radius, which I'll consider my green radius, is going to go from the center to the closer curve. So from the center to the closer curve would be sine x. And so if I follow the rules here, the rule says if I want to find the volume of the solid, the volume is pi times the integral from a to b. Well, where do cosine and sine intersect? They intersect at 0 and pi over 4, which was given to us in the problem as well. 0 to pi over 4. You might also notice that I pulled the pi out in front. You don't have to do that. I do sometimes, I don't other times. It just depends. All right, so I pulled the pie out in front. Now I need capital R minus lowercase r, which stands for outer radius, or bigger radius, squared, minus smaller radius, squared, dx. I don't know why I gave one parentheses and one not. It doesn't really matter, but that is the correct answer. The volume of that solid is the integral from a to b of pi capital R squared minus lowercase r squared. Outer radius squared minus inner radius squared. And then if I come over here to my calculator, I'm going to do a pi and then a math 9, 0 to pi over 4. I'm going to be very careful in here now. I need to put the parentheses in here to square the cosine. Minus sine x squared dx. Da-da-da. And this is 1.570. Now, quick note on your calculator, this is just me. I really like to know where that squared is, so when I square cosine, I always do a double parenthesis here. Technically, you can square cosine like that, but you can also square it like this. No, that's not what I wanted. Come on. Go over here. There we go. You can also square it like this. The reason I don't like doing that is because a lot of times that's going to make you think that this is the cosine of x squared, and it's not. This is the cosine of x squared. So just be careful how you square your cosine. Technically, you can do it right after that parenthesis that ends the angle. But personally, I like to add that extra redundant parenthesis just because it makes me feeling better. I don't really care what you guys do, but just FYI, technically this is cosine squared x. And that's the answer. Okay, I digress. So let me pick up the pace here because I've already wasted a lot of your time. Look at that, 7 minutes. Long story short, the volume of a solid that's got a hole in it is capital R squared minus lowercase r squared dx with a pi out in front. Okay? So find the volume of a solid created when the region enclosed by y equals x squared and y equals x. Wow, that's terrible. Close enough. When this region right here is spun around the x-axis. Okay, so if I spin that around the x-axis, it's totally going to have a hole because I have this representative rectangle. It's going to go whoop, spin around. And so my disk looks like this. It's got a little edge to it. And my outer radius goes from the x-axis up to the furthermost curve from the x-axis. So from here to that, which is y equals x. And then my inner radius goes from here to the bottom curve, which is x squared. So the volume of the thing that I get when I spin this around the x-axis is pi times the integral from 0 to 1, trust me on that, of outer radius squared minus inner radius squared dx. Ta-da! There you go. There's your volume. So very quickly, let me just get an answer here so that we have one. Second pi math 9 0 to 1. I know this is exceedingly exciting for you guys. So what do porcupines say when they kiss? Ouch! Oh, I know it's a terrible joke, but you laughed a little. Admit it, you laughed a little. There we go. What kind of bow can't be tied? A rainbow! I'm hilarious. There we go. Look at that. 0.418. Remember, you can truncate or round. I tend to truncate. There's your answer. Find the volume of the solid when that same region is revolved about the y-axis. So now I have this, and I'm going to spin it around the y-axis. So anytime I'm going around the y-axis, I need to make my rectangles look like that, and I'm going to spin them this way. So now my discs look like this with a little bit of depth to them, or my washers I should call them. My discs with a hole look a little bit like that. And my outer radius goes from the y-axis to the curve furthest away. So that curve is y equals x squared But since I'm spinning around the y-axis, it needs to be x equals the square root of y. So my outer radius goes from here to the square root of y, and my inner radius goes from the axis to the line, which is y equals x, also known as x equals y. So the volume of my solid is going to be pi times the integral from 0 to 1, because these intersect at 1, 1, and 0, 0. So that's a 1. Pi times the integral from 0 to 1 of outer radius squared minus inner radius squared. And that is your volume now. So very quickly, let's see how much that differs from the other one. I'm just going to use everything from the other one anyway because my bounds are the same. And instead of having an x squared first, if I can actually get over here, I really just have an x. Go away. And over here, I would have an x squared. Let's see if it yells at me because of that missing box. Oh, come on. Stupid math print. Go away box. There we go. And this one is 0.523. Now, why are those volumes not the same? Because I'm spinning around different axes. This is closer to the x-axis, so it's got a little bit less volume. This is further from the y-axis, so it's a little bit wider when it spins. All right. All right, last but not least, we have these. I really want you to try some of these on your own. What are we at minute-wise? We're at 11 minutes. This should take you by yourself maybe 6 minutes. Just set up the integral, plug it into your calculator, and get an answer, all right? So I want you to set up these integrals, and while you're doing that, look, I've got your intersections for you right here if you want them, or you can store it in your calculator as well. So take a second, look this over, and I want you to try to do A through D on your own. One or two of these has a little bit of something unique going on here, but do it anyway. All right, I'm going to hit pause, and then we'll come back and regroup. All right, so I hope you at least try to do these on your own and you don't just leave it for me, but here you go. If you take R here and rotate it about the x-axis, what happens is you need to split it up into two regions. You have the region from 0 to a and the region from a to cube root of 2. And from 0 to a, you're spinning tan. And from a to the cube root of 2, you're spinning the cubic. This is not a washer problem. This is actually a disk problem. There is no hole because R is flush with the x-axis. So if I spin R around the x-axis, I get 1.142 as an answer. Now, if I then take R and spin it around the y-axis, I do have a hole. This area right here ends up making a hole. So my outer radius goes from the y-axis to the cube function, which really becomes a cube root in terms of y. And then my inner function becomes inverse tan y. And since I'm spinning around the y-axis, I have to be in terms of y. So I take this region from 0 to b and do pi outer radius squared minus inner radius squared and get 3.4488. If I take S and I spin it around the x-axis, that has a hole. This is another bundt cake looking kind of thing. So if I spin S around the x-axis, my outer radius goes from the x-axis to the cubic, and then from the x-axis to tangent. So pi outer radius squared minus inner radius squared from 0 to a 8.331. And last but not least, if S is revolved around the y-axis, it is solid, but it needs to be split up into two regions, from 0 to b, and then from b to 2. So from 0 to b, I'm spinning the tangent graph, so inverse tan y. And from b to 2, I'm spinning the cube root, 2.495. And that is really that. So, long story short, when you are finding volumes of solids of revolutions or solids that come up out of the page, you find the area formula for the face, stick a dx at the end. In our case, when you do solids of revolution, this area becomes pi r squared, or maybe pi capital R squared minus pi times the lowercase r squared. And that is that. So hopefully everything made sense. Come to me tomorrow with questions if you have them, and toodles.